So we start, and today is unlike any other lecture really. We'll just do a sort of whistle tour stop of various things you have already seen, possibly just beyond your horizon so far. And the idea is to flesh out some things that we'll need then throughout the course. Okay. So first, let's talk about simple symmetric random walk. So you'd have all seen this. S0 is equal to 0, and then Sn is equal to sum from k equals 1 to n x k, and then I'll have x k's id random variables, and those represent steps up and down. So probability that x k is equal to plus 1 is equal to a half. Probability that x k is equal to minus 1. So clearly what's happening is that my walk takes a step up, step down, step up, step down, step down, step down, step up, and so it continues. Okay, it's a sum of IID random variables, and we've already learned quite a lot about these sums throughout the years. So the first thing that you know is that if you look at the empirical mean, so I look at the sum of first n variables and divide it by n, then this converges. Okay, it converges to the mean of each of these random variables, which in this case is 0. So I've this small code, which is online, just simulates simple symmetric random walk. So I'm doing 1 million steps, and I'm doing 30 paths. Okay. And so this first plot just shows us that we indeed converge to 0. Okay. Now, in what sense do we converge to 0? The easy statement that you would have had in prelims will be to say that this converges in probability. So this would be saying that probability that Sn divided by n is greater than epsilon, this goes to 0 as n goes to infinity, and this is true for any epsilon greater than 0. Okay? Now this makes no sense unless I make this slightly larger. So that's in probability. That's quite easy to show. But what's also true is that this convergence happens almost surely. And that's a much more difficult statement. Okay? You sort of, your statistics depend on that. But this is 1800, so this is 1713, maybe Bernoulli's first proof of this, and this goes to 1930s. Okay, so Kolmogorov and Khinchin. So a good 300 years in between. One of the things we will do in this course is that we'll prove this statement. Okay, we'll prove that a sum of IID random variables converges to the empirical mean, converges to their actual mean almost surely. It will take us a whole course to get there. Okay, so this might be the penultimate lecture where we'll actually prove this. As in a lot of things with this course, we'll spend a long time developing tools, and then once we have the proper tools, we'll be proving things in 4 lines, time and again. Okay, but we'll spend quite a long time developing the tools. So you would have seen those results. Now, of course, as a mathematician, your next question is, well, if I know that this converges to 0, then I would like to know how fast this converges to 0. Okay, so what does it mean? It means that I'm going to look at Sn divided by n, and I'm going to multiply it by something that goes, so this goes to 0. I'm going to multiply it by something that goes to infinity so that I get a non-trivial limit. And this something is square root of n, and then I know that this converges to a Gaussian random variable in distribution. Okay. So here we are clearly converging to 0, just plotting Sn divided by n. Now I'm going to plot Sn divided by square root of n. Okay, so each term gets multiplied by square root of n. And what does this mean? This means that probability that this Sn now divided by square root of n. If I want this to be greater than phi minus 1 of something, what is phi minus 1? Well, I'm going to look at the Gaussian random variable. Okay, and I'm going to take a number. This is phi minus 1 of, let's say, 0.005. Then I get 10% in total here. This is 0.95. And I get 10%. I took absolute value there, right? So I've plotted 2 lines here. This is the red line, dotted line, corresponds to the Gaussian CDF at 0.98. So I should be getting about 4% that breach the red lines. These are 30 paths, so 4% of 30 paths, that's about 1.2 paths, so just over 1 path. There's one, you see the sort of black path that just about touches the red lines. The greens are what I wrote there, so it should be about 10%, so about 4 paths breaching the green lines. And as it happened in this simulation, I get the black, orange, and then the 2 ones at the bottom. So I did get exactly this. Okay. But this, of course, means that rare as it is, there will be some paths, because this is a Gaussian random variable. You know, the tails are, this is not a good drawing, the tails go to 0 very fast. But nevertheless, there's some positive probability of finding things very far away there. So even though we're not seeing them here, if I was plotting sort of 30 paths, if I was plotting a million paths, then, you know, the paths, there will be an odd one which would go really far up. And so I would like to understand better what this means. So this was known as strong law of large numbers. Okay. This result here is known as CLT, the central limit theorem. So now I need something a little bit more precise. Okay. I would like a statement that will tell me how. So I know that some of these paths here will nevertheless grow to infinity, and I would like to control exactly how that is. Okay. So I have this, and I still need to divide it by something that goes to infinity, just to dampen those very rare paths. Okay. And the right scaling will be log n. Okay. And it turns out that if you do this, so let me plot that for you. Now this is now a non-trivial quantity, so this will not have a limit. It will have a lim sup, which will be equal to square root of 2, and we'll have a lim inf, which will be equal to minus square root of 2. Everything has to be symmetric. Okay. So now I'm dividing, instead of dividing by square root of n, I'm dividing by square root of n and then log n. And I'm plotting the minus and plus square root of 2. But I'm still just going out into a million steps. And this is really an asymptotic result. To see how it works, you should run it for much longer. You have the codes, it's very easy to modify that. Okay? But this is now a really fine result. This is the law of iterated logarithm. Log n. Okay? This really tells you something very specific about the behavior of your random walk. We might prove this, just about. Depends how I structure the last 2 or 3 lectures. But you will have tools to prove that. Okay? And this is quite a fine result. Another way to visualize that is to just plot the random walk. And then the red line is the blue line is the CLT, square root of n, and the red line is the square root of n times log n. Okay, and you see how they grow. So in this course, we'll reiterate a little bit how the difference convergence properties work. Okay, we will prove this result under no other assumptions than just assuming that these random variables are integrable. We're not going to go back to CLT, not much at least, but we will talk about convergence in distribution, and we'll have enough tools to prove this. Okay. Let me switch off the small visualization. And let's now talk about another process. So this was simple symmetric random walk. This will be now a branching process. So what do I mean by a branching process? I start with one individual, and this individual will have offspring. Okay? So you'd have seen this in part A probability. So maybe they just had one kid. Okay? But then this individual also has offspring, and maybe they had 3 children. Now this child did not have any offsprings, they died. But this one was very prolific and had lots of kids. And this one maybe just had 2, and so on we go. Okay, so that's the idea, is that each individual or bacteria, whatever it is, has certain number of offsprings. They're all independent of each other, but the distribution of number of offsprings is common. Okay? And we'd like to understand whether this process, how it behaves long term, whether it dies out, or if we can understand some fine properties of this Galton-Watson branching process. So let's try to define this property mathematically. So this is definition 0.1, the Galton-Watson branching process. So if you think about this, well, my definition was that Z0 was 1. And then what was Zn? Well, Zn was the number of individuals in the nth generation. And how many are there? Well, I have to look at the previous generation and then allow each of them to have offsprings. So I just need some notation. And this notation will be x here. So what are x's? X's will be just all IID. So I have a large array. So nk. These are all IID random variables. So independent with identical distribution. So x1, 1 has distribution x. And this is something that takes values in 0, 1, 2, etc. Probability that x is equal to k is equal to pk. Okay. So that's my distribution. And what did I do here? The number of bacteria in the nth generation, I look at everybody in the nth minus 1 generation and allow them to multiply. Okay? So this is a sum of random variables, but the number of random variables I'm summing is random itself and controlled by the number of bacteria in the previous generation. I claim that that makes sense, and this allows me to define the process. So now I'm going to study this process. This distribution is, of course, key, so I'll look at some of its properties, and I will do so by looking at the generating function. Okay. So I'll write f, or fx, of theta. This will be expectation of theta to x. Okay. So you know this function. We've sort of studied these functions. This is the probability generating function. So what I mean by this is the sum of k equals 0 to infinity, and I have theta to k pk. Right? What are properties of this function? Well, f of 1, this is just expectation of 1 to power x, so this is 1. F of 0, this is by convention 0 to x, will be either 0 except 0 to 0 will be 1. So this is p0, probability that I take value 0. Then what else we can remember about this f prime of 1? If you expand this, this will be equal to m, which is the mean of x. Okay. So I can write this also as sum of k pk. So this will be a useful object to study this process. So the first claim, I'm not really making any proper statements because I not really defining things properly today. Okay, but the first claim is that if I look at function fn of theta, and this will be the probability generating function of Zn. Okay. So just like here, this was the probability generating function of one variable x. Here I have the probability generating function of Zn. I claim then this is the n-fold convolution of the function f. Okay. And how would we sort of prove it? Sketch of ideas, if you want. Well, f1 of theta, this is equal to expectation of theta to z1. This is expectation of theta of x1, 1. My z0 was 1, and so this is just equal to fx. And I'm done. And what would be expectation of theta of Zn conditionally on Zn minus 1 equal to k? Okay. If this makes sense, let's just try to sort of reason for a moment. Well, if I know that I had k individuals in the previous generation, this object, which was a sum with random number of elements, now becomes just a sum of k independent, identically distributed random variables. So I no longer have any dependence on the history. This is just equal to expectation of theta of x n1 plus x n k. And of course now this, they're all independent, so this is just expectation of theta of x n1 times. And all of these are the same. Okay? This is nothing else but f of theta to power k, because each of these is f of theta. So now I can observe that I have this k here, and I had k here. And what I want to say is that really I can think of expectation of theta to Zn conditionally on Zn minus 1, and this ought to be a random variable itself, which should be given by this formula. Okay, so now I'm looking at conditional expectation. So what should be my expectation of this object, knowing Zn minus 1 and not fixing the value of it? Well, of course, the answer will be a function of Z minus 1, and it will be given by this. Okay. And now I think that if I want to compute this object, which is what I'm interested in, then I should be able to first condition on some information and then average this conditioning. Okay. And if I do this, I get expectation of f of theta Zn minus 1. And this is nothing else but the probability generating function of Zn minus 1 in f of theta. So this is fn minus 1 of f of theta, which proves now things by induction. Okay. Now what did I do here? This property here will be known as the tower property. And understanding properly how to define such objects will be one of the key elements of this course. Okay, so we'll spend quite some time first building the language to even start properly talking about them, and then actually defining and proving existence and properties of objects like that. Okay? This will be the conditional expectation. We're going to completely dump this sort of baby version of conditional probability, which was a number, and we'll be thinking of conditioning as something that involves us making approximations using smaller sets of information. In fact, information is going to be something that will be very important for us, and we'll talk a lot about how to model information. Okay? So this will mean I'm going to try to understand what this variable might be given certain information generated by the previous generation, and that will be that. Okay? Good. So let's make another claim. This is claim 0.3 now. Let Q be the probability of extinction. Let Q be probability that Zn is equal to 0 for some n. Now, of course, if you become extinct at some point, then you continue to be extinct. There's no resurrection in this game, right? So this is the same as probability that Zn is equal to 0 for n large enough, where large enough means from some point onwards. And then let's also assume that P1 is less than 1. If P1 is equal to 1, that means that you always have exactly one offspring, and the population is just constant, always equal to 1. It's a very boring case. Okay? So if this holds, then what do we claim? We claim that there are two possibilities. If m is less or equal than 1, then Q is equal to 1, so the population will become extinct. And if m is greater than 1, then Q is strictly less than 1. There is a positive probability that the population will survive forever. You saw this in part 10, right? What was the proof? Well, the proof is really the following. We can characterize this Q Q is the smallest root to the equation f of Q equals to Q. Why is this true? Well, if I let Qn be probability that Zn is equal to 0, then this is of course an increasing function. That's because Zn of 0 is a smaller set that Zn plus 1 is equal to 0. Once I'm dead forever, but I could be still alive and die afterwards. Right? So that means that this is an increasing function. And probability Zn is equal to 0, this is nothing else but Fn of 0, right? The probability generating function at 0. This is the property that we had there. So this is now the same as Fn minus 1. Maybe let me just write it like that. This is the same as f of Fn minus 1 of 0. And now intuitively, this Qn now is increasing, so it converges to something. It's increasing, and of course, is less or equal than 1. So it has to converge to a number, and somehow intuitively Qn should converge to Q, probability that Zn is equal to 0 for some n, which was defined there. So this is Qn is equal to f of Qn minus 1. Well, this converges to Q, and this converges to f of Q. So that shows that Q has to solve that equation. And of course, you can have this intuitive picture in mind. We started with here f of 0. This was my function f, and this is f of 0. So this is f of 0. This is an identity map. This is f of 0. So this is f of 0. And this is f of 0. This is f of 0, etc. Right? So I keep climbing this staircase, and I either get to this point, or there is no point like that, because my function never intersects the identity, the diagonal before, and it's just doing this, in which case I climb all the way to here. In this case, Q is less than 1. In this case, it's equal to 1. How do I distinguish these two cases? Well, I just have to look at the gradient of this function at point 1. And if the gradient is greater than 1, that means I'm coming from below. And if it's less or equal to 1, that means that I'm coming from above. Okay? Which is precisely what I wrote there, because m is the gradient of f in 0. So that completes the proof, provided we can sort of make sense of everything there. Okay, and it's quite intuitive for the case m less than 1 and m greater than 1. The case m equals 1, the fact that you will get extinction is non-trivial. But then, of course, we would like to understand more. We'd like to understand how fast this extinction happens. What really, what are the real dynamics of this process? Let's try to compute a little bit more. Just like we did here. Okay. Let's try to compute the expectation of my population, assuming that I had k individuals in the previous generation. Well, this is easy, right? This would be x n plus 1, 1. And just like before, now this knowledge doesn't really matter for me, because all of these are independent NIID. And by linearity of expectation, I would hope that this is the same as just simple expectation. And then this should be just k times expectation of x. So this is k times m. Right? So here I'm using linearity. So this operator, this expectation, should really have this property. We saw this, of course, you saw this in probability so far. You also saw this in integration, for those of you who have done integration. Great, so let me try to do the same trick as I did there. So now I'm just going to write expectation of Zn plus 1 given Zn, k, so this should be m times Zn. And I could sort of continue this, right? I could condition on Zn minus 1, etc., etc. So in particular, from here, I see that expectation of Zn plus 1 is equal to m times expectation of Zn is equal to m squared expectation of Zn minus 1, etc., etc., is equal to m n plus 1. So let's try to normalize this. So let mn be equal to Zn divided by mn. What happens if I do this and I compute expectation of mn given the past? Okay. So in the past, it means I know all the previous mn's, mk's, which is the same as knowing previous zk's, because this is just a constant. So this is expectation of Zn divided by mn given the past. So in particular, I know the previous value, and that already tells me that this will be equal to m times Zn minus 1 divided by Mn. Okay? From this property here. Now, of course, this cancels out, and I get Mn minus 1. So that really means that somehow my best prediction for where I will be tomorrow, given everything that happened so far, is where I'm today. Such a process will be called a martingale. It's in the title, so you can guess that it will be important for us. In particular, we'll study convergence of these processes, and we will see that this has to converge to M infinity almost surely. Now, if M is less or equal than 1, then I know that Zn is equal to 0 for n large enough. And of course, if z is 0, then m is also 0. So that means that the only limiting value can be 0. Okay. And that's sort of interesting because you see that expectation of Mn is equal to 1, is independent of n, and clearly is not equal to the expectation of limits of Mn, which will be equal to 0 in this case. This should remind you of the Fatou lemma in integration. Okay? And we'll also see an instance of this later. So when you're done with this course, you should go back to this couple of boards and make sure that that you can actually understand every step properly. So I'm writing a bunch of symbols and trying to somehow hopefully convince you that they all make sense, and you've sort of seen them in part A, so hopefully they make sense. But we don't really know what that means, right? We haven't actually defined this in any proper way. And what we'll see is that there is a proper way to define this, and that these equalities will indeed hold. Let me give you another example. So, linked to mathematical finance. So for those of you doing B83, this will be just somehow like a recap of what some of the results in that course. Okay, so let's imagine that we are investing in the stock market. Okay. So I have some stock price, Sn, models this stock price. And I'm going to buy and sell these stocks. Okay, so what does it mean? I'm sitting here at time n, and I have some cash. Maybe let's call my cash Vn. Okay. And then I can also have some shares. I can decide to buy shares. So suppose I want to buy Hn shares. Now this Hn, of course, could be a function of the past, of the past prices. And then time goes on, and I get to n plus 1. What happens with the cash? Well, if I bought these shares, then I had to borrow money to do this. Okay? So that means that I subtracted Hn times Sn. This is how much Hn shares costed at time n. This could be positive or negative number, I don't know. So either I'm getting interest from the bank or I'm paying interest on the loan. But suppose there is a interest rate R. Okay? So that means that my cash is now Vn minus Hn times Sn times 1 plus R. Okay? Either my loan got more, I either accrued interest for me or against me. Now, what happened to my shares? Well, nothing happened. I still have the same number of shares. But now I can sell them. Okay? So if I combine these two positions, that means that my new wealth, my new cash, will be equal to this. And then plus Hn times Sn plus 1, because I'm selling at the new price. So let's rewrite this in terms of discounted quantities. So let Vn tilde be equal to 1 plus r minus n times Vn. And likewise, Sn tilde will be 1 plus r minus n Sn. This 1 plus r to minus n, that corresponds to the value today of $1, 1 pound, whatever your currency is, 1 Bitcoin in n times. So if I rewrite this equation there, what do I get? I get that Vn plus 1 tilde. So I have to divide everything but by 1 plus r to power n plus 1. I had 1 plus r here, so I'm just going to get 1 plus r to power minus n, which will hit here and here with a tilde. So I'm going to get Vn tilde minus Hn Sn tilde. And then here I have Sn plus 1. I'm dividing by 1 plus r to power minus n plus 1. So this is all correct. So I get Sn plus 1 tilde. Okay. So I can write this as Hn Sn plus 1 tilde minus Sn tilde plus Vn. Okay. I combine these two terms here, and that's my wealth. And now, of course, this is a telescoping sum, so you can continue. And what do you get at? You get at V0. V0 is the same as V0 tilde. There's nothing there. And then plus sum of HK S tilde k plus 1 minus S tilde k. And now k goes from 0 to n. Object like that, you see clearly what's happening. Integrand, integrator, right? This is a discrete approximation to some sort of integral. Looks like this, looks like Riemann sum. And this is sort of Riemann sum. This is a discrete stochastic integral. And those of you doing the BH2 next term will study how to take limits when this is a discretization of a continuous stochastic process. In this course, we'll stay in discrete time. Okay? Sometimes this stochastic integral is also called martingale transform. It's called martingale transform because if this is a martingale, then this process is also a martingale. Now, why is this interesting? So a typical question in mathematical finance would be, what is the fair price today? So n equals 0, let's say, for a cash flow. So some payment, let's call this f of S0, S1, Sn at time n. How much should I pay today to somebody who's willing to provide me some random payoff in the future? And the idea, going back to Black and Scholes, would be that this is really the sort of economics basic law of one price. If you have two ways to achieve the same cash flow, then they should have the same price or the same value. And so the idea is that if there exists a V0 and H such that Vn is equal to F, that means that I can start with some capital and then use trading in the shares to replicate that future cash flow, then V0 is the fair price. If somebody is willing to sell this for less, I will happily buy it, take some money, invest in this and replicate. So either if it's more expensive or less expensive, I will either buy or sell. But I have another way to achieve the same payoff at price V0. And so the question, and this is sometimes possible, okay? And the question is, how do you compute that? Well, it turns out that this is a complicated object, but if S tilde was a martingale and I took expectation, and this whole thing would disappear and expectation would just be V0, because this would again be a martingale just like I had there. So this is the idea in math finance, is to find such strategies and allow it to construct payoff pricing strategies. So this is now proposition, but you can prove it easily in a couple of weeks' time, but this will be the following. Suppose there exists two constant d0 such that 1 minus d, 1 plus r, 1 plus u, and such that Sn is either equal to 1 minus d times Sn minus 1 or 1 plus u Sn minus 1. So what am I writing here? I'm just writing a recombining tree. I start here and I go to here, 1 plus u as 0, 1 minus d as 0, and then I go up or down, down, up. Etc. Right? This is called the binomial recombining tree. Each time you go by the same multiplier down or up. Then for any such f, there exists a v0 and h such that v tilde n is equal vn is equal to f. Okay. And furthermore, there exists a unique Q probability measure such that S tilde is a Q martingale. And this V0 is equal to expectation, now under measure Q of, 1 plus r minus nf. Why am I writing this? Because see, this beautiful another notion appears here, which is a change of measure. So I didn't tell you where things were defined at all and how they existed, but somewhere there we had a probability measure, omega fp. You saw this in part A probability. And what I'm saying now is that instead of this probability measure, which I had, I'm defining a new probability measure. I'm looking at the same process, but now this process becomes a martingale under a new measure, and I can use this to compute things. And we'll develop language to allow us to construct probability measures and to build new probability measures from existing probability measures, including understanding how this interplays with the martingale theory. In fact, we'll really be looking how to define things properly. Okay? So you can think of integration as a playground where we just toyed with Lebesgue measure. Okay? Now we're going to really be thinking of all measures, because if I have some omega fp, okay, and I have my random variable, this is a picture you're used to. Okay? I can now define measure mu x. Here, this is the distribution of x. And what does it mean to take expectation of x? Well, that should be an integral on this space of x of omega with respect to the probability measure here. We will define this so that we can make sense of this object. But equally, this expectation, of course, is just the mean, is the property of the distribution. So I should be able to just integrate here. And what does integrating here? Means I'm integrating over r, x, mu x, dx. Okay? And I want to make sense of these chains of spaces and integration on different spaces and making sure I connect integrals. Okay? You've computed expectation in all of these ways. In fact, when we study existence of probability measures, we'll also answer this existential question, I'm sure a lot of you had, is do these objects exist? When you say let xn be a sequence of IID random variables, something you've been using for quite some time, so far, essentially, you have no idea whether this exists, whether you can actually do that. Okay? So that's what we're going to do for the rest of the term. And as I said, next couple of weeks, we'll spend building the language of measure theory in order to be able to do all of that. Thank you so much, and I'll see you tomorrow.